Hello everyone, my name is Akshat Jain and this is a PPT video on visperlm elevating visual perception in multimodal LLMs, and this is the paper published in Europe 2025. It is the work that is done between the SHI Labs, Microsoft Research and Meta Superintelligence Labs. So, so what are the challenges we are facing? So this is the problem statement of the paper. Uh, The challenge here is how to build a multimodal large language model that excel at visual perception tasks, particularly spatial reasoning and depth estimation, while maintaining the efficiency needed for real world deployment. So our approach uses visual embedding distillation to enhance spatial reasoning, and I will walk you through how we state the sort of performance with a surprisingly efficient architecture. So let me start. Let me start by explaining the problem we are solving. So currently, multimodal LLMs follow a fairly standard architecture. They connect vision encoders to large language models through a simple projection layer. They optimize primarily using next token prediction, essentially a language-centric objective. While this approach works well for language understanding, it creates three critical weaknesses. First, these models exhibit poor spatial reasoning. Second, inadequate performance on embedded AI tasks. Third, limited 3D understanding capabilities. Now, existing solutions are like Cambrian one attempt to fix this by throwing more encoders at the problem using four or more vision encoders. And yes, this does improve perception, but it comes with severe computation cost. 1.86 times higher inference latency, massive training dataset requirement, and substantial memory and computational overhead. So the research question here, can we achieve a strong visual perception with single encoder efficiency? So our core discovery, the internal representation hypothesis. Our breakthrough came from fundamental insight about how these models actually work. We hypothesize scaling visual inputs and training data improves performance, but not because you are feeding in more encoders, but because you are enhancing the quality of visual representation inside the LLM itself. So to test, we conducted extensive probing analysis, and what we found, we discovered an correlation 0.98 between internal representation quality and VQA performance. We also found that middle layers, specifically between layer 12 to 24, exhibit optimal representation quality. And importantly, more training data systematically improves these internal representations. So, what is the breakthrough insight? Instead of feeding multiple visual inputs at inference time, we can directly optimize the visual quality of LLM's internal representation during training, achieving multi-encoder benefits with single encoder efficiency. So, what is the architecture that we have worked upon? So, how this Whisper LM work? The key innovation is the training time distillation. During training, we employ auxiliary expert encoders alongside embedding predictors to distill specialized visual knowledge directly into the LLM's intermediate representation. This enriches the model's internal understanding of depth, segmentation, and visual generation. Second is that at inference time we use only single encoder. No auxiliary components are required. The LLM has internalized the visual expertise during the training, so we can deploy it with very little computational overhead. So if we see, we use three expert knowledge sources, each with their own spatial token for depth understanding. These spatial token for depth understanding, Dino V2L from depth anything. We use a token D for segmentation S for visual generation G. What are the system components and design? So first is the base vision encoder. The base vision encoder we use either clip VIT large or clip connext extra large processes input image into feature representation. Second is MLP projector. MLP projector aligns these visual features with language model embedding space. Third is decoder LLM like Llama 3 8 billion or 4K mini serves as the core reasoning engine. Fourth is the embedding predictors. Training only this component is used. Single layer perceiver resamplers at selected LLM layers. Predict expert embeddings. For learnable queries configuration, the configurations are mentioned below. And for the optimal layer selection, based on a probing analysis, depth is layer between 8 to 20, segmentation layer 10 to 18, and generation layer 12 to 20. Token sequence formats are given below. So this is the architecture that we use. You can see the base vision encoder, the MLP projector, the embedding predictor also. And we use the text cross entropy loss and the token sequence format you can see here below. This is the token sequence format we have used. And you can see like this is the whole architecture of our visperlm. So what is the multi-stage training methodology that we have used? The stage one is pre-training. So dataset Lava 558K is used objective combined next token prediction embedding distillation losses. Enable MLP projector component, embedding predictor component, and special task token. Frozen are base encoder and LLM backbone. This stage teaches the model to build rich internal visual representation. Stage 2 is instruction fine-tuning. And our dataset is used is Lava 665K. Objective, next token prediction only. No embedding losses. Trainable components are projector component and LLM parameters. So here frozen are base encoder and special tokens. So here are the pre-training loss function looks like. So here we combine the next token prediction with three embedding losses, one for each expert signal. We set lambda to zero point 0.5 for all three, balancing language modeling visual representation quality. Each embedding loss combines smooth L1 and contrastive objectives. So visual perception performance that we have done this experiment on the CV bench and results are below. So what is the results here? We have used the Llama 3 8 billion plus Clipchamp next XSL configuration. So on counting tasks, we gain 3.3 percentage. On depth estimation, which is particularly important for robotics tasks, we achieve massive 8.7% improvement, going from 62.8 to 71.5 percentage. On the relation task, uh, shows a small decrease which we attribute to the model specializing in certain spatial reasoning aspects, but the overall gains far outweigh this minor trade-off. Distance reasoning improves by 3% and overall we gain 2% on average. So this demonstrates we have successfully internalized multi-encoder benefits without the inference time computational overhead. We are getting the best of the both worlds. Efficiency without compromise. So we have done the work on the efficiency. One of the most compelling aspects of Whisper LM is that we achieve these perception gains without any efficiency trade-offs. So on NVIDIA A180GB GPU, we have a throughput of 9.86 samples per second, 5.32 multi-encoder throughput, 46% slower inference speed, speed advantage 86% faster than multi-encoder baselines. No degradation in the general reasoning also. Did we sacrifice language understanding of visual perception? Not at all. The chart shows performance. As you can see in the chart, there are different uh, benchmarks, multimodal benchmarks, MM star, WizWiz, GQ, and POP. visperlm maintains or slightly improves performance on all of them. Wiz is in particular shows a 3.4% improvement, which makes sense given its visual grounding requirements. The key takeaways is that enhanced visual perception does not compromise general reasoning capabilities. we get improvements across the board. So if we come on the Blink benchmark, which test visual perception in a different way from CV bench. So if we see the results here, results are even more striking. visperlm achieves 58.8% average score, which is overall the best performance among all methods tested. We improved by 3.5% over Llama 1.5 on a spatial relation task, going from 72% to 75.5%. On counting task, 5.9% improvement. Relative depth performance is competitive at 51.6%, matching Cambrian 1 despite using only single encoder. What's important note here is the strong generalization to a specialized perception benchmarks. We are not just overfitting to CV bench, the improvements transfer to different evaluation paradigms. So these are the key achievements. We have gained a very important and a very efficient scores in different types of evaluation paradigms. If we come on the loss function components, which drive the performance gain, contrastive loss impact. Adding contrastive loss to the baseline smooth L1 objective yields measurable improvements across vision-centric benchmarks. As you can see, we have got 1.6% absolute improvement here. And multi-target embedding strategy. What is a multi-target embedding strategy is where things gets really interesting. We tested each expert single individually. Depth only gives 53.6. Generative feature only gets 53.8. But when we combine all three, we achieve 54.1. So key finding, all three target features contribute unique complementary information that collectively enhance visual reasoning capabilities. So what is the probing analysis reveals? So our methodology involves training lightweight single layer probes at each LLM layer to assess visual representation quality. We extract target features from our three specialized experts encoder, evaluate using cosine similarity on COCO eval. So what we discovered, middle layers 12 to 24 demonstrate optimal visual representation quality. Their distinct performance peak in this range. This suggests that these intermediate layers naturally encode spatial and perceptual information most effectively. They are not too early where features are still low level, and not too late what the model is focused on language generation. It is in between. And the remarkably strong R equal to 0.98 between depth probing performance and downstream CV bench accuracy, validating that internal representation directly predict task level performance. And data scaling effects. Increasing data improves reasoning representation quality. Even when with standard next token prediction training, visperlm positions between single and multi encoder baselines while maintaining a single encoder inference efficiency. So we have got a maximum efficiency with a single encoder. So these are the results on the probing analysis. As you can see, we have used a cosine similarity in the COCO dataset, and visperlm falls between the multi-encoder and single encoder baseline, serving as a trade-off between efficiency and represent quality, as you can see here in these charts. And second, the scaling training data. So in the scaling training data, with more data shows improved performance, as you can see in the charts. So we measured the projector quality also. So after pre-training, by computing cosine similarity with the target features, the base clip connext XSL encoder achieves 0.592 average with our average similarity. The standard lava 1.5 projector gets 0.602. So, but our Vispa LM projector reaches 0.611. As you can see in here, 0.611 we got on average, which is a 0.9% average. Uh, might sound small, but remember, this is after only the pre-training stage. We have done another stage after that. This better visual language alignment from earliest training stages establishes stronger foundation for multimodal reasoning. What is the downstream impact? Superior projector quality translates directly to better visual language alignment through instruction fine-tuning, stabilize stronger foundation for multimodal reasoning, scalability validated with extended pre-training data. So what we have done, we wanted to validate that our approach scales with more training data. So we have done experimentation with our Lava caption 663K dataset, and we have used 534K mini clip VITL results. And with these results, we got strong gains, plus 4 performance in the counting, plus 2% performance in the depth perception. As you can see, the gains are here in overall all areas. Comparative analysis. So positioning against the SOTA, and if we talk about the encoder distillation. So encoder distillation methods like radio VITL. Single encoder influence 55.1% CV bench average. Pre-distilled vision encoder approach. This is multi-encoder Cambrian. LLM distillation that is ours 57.6% CV bench average, which is greater than both encoder distillation multi-encoder method. We have used the LLM distillation. So encoder free VLM comparison, if we see the Chameleon 39.6, EVE 58.4, and visperlm 61.5% is overall. So encoder enhanced performance we can see here in our architecture. So if we say about the encoder flexibility, Whispers LLM's effectiveness generalized across fundamentally different vision backbone architectures, demonstrating that the approach is architecture agnostic and broadly applicable. So if we test with the Cambrian's one, top ranked encoder validates cross architecture compatibility in the relation in the depth, average, and count. We have got our standard VIT clip VITL, standard VIT architecture plus 2.5% improvement, strong baseline compatibility. In the XSL, it is a plus 2% improvement. In the SIGLIP, it is a plus 1% improvement of SOTA encoder. So, key insight here is the consistent gains across different architectures confirm that Whisper LLM's predictive embedding frameworks successfully transfer visual knowledge regardless of what is the encoder design. So, this is the architecture agnostic approach. So, what are the contribution here is first is the semantic analysis. We have done a correlation. We have stabilized a correlation between LLM's internal visual implementation and downstream task performance. The layer-wise probing reveals middle layers are optimal for encoding visual information. Novel training paradigms. So we have used two types of training, two sequential training approaches. So one is the pre-training, then is the instruction fine-tuning. So vision-centric training complements traditional language-centric next token prediction. Predictive embedding architecture inspired by iJPA, self-supervised learning framework. Perceiver resampler with task-specific learnable queries enables strategic layer selection based on empirical probing insights. Spatial task token we have used. You can see like they are depends task on the task specified task. So it tune using the task specific information prevent catastrophic forgetting, which is very common during the fine tuning, but we prevented that. So what are the real world impacts? So in the robotics, 8.7% improvement in the depth perception. So we can do more accurate distance estimation for collision avoidance and path planning. And resource constant deployment, we can do 86% faster inference compared to multi-encoder approaches. We can deploy it on a edge devices. Research methodology contributions are decision architect systematically architecture agnostic approach. So it stabilizes a new framework. Vision centric training paradigms here demonstrate that specialized vision knowledge can be effectively integrated without sacrificing language understanding or general reasoning capabilities. And no trade off design. This is a no trade off design. Maintaining computation efficiency and preserving reasoning capabilities, which are rare combination in multimodal learning. So limitations and future directions are the task scope. primarily focus on spatial and depth reasoning tasks. Broader visual reasoning capabilities remain underexplored. They are language reasoning capabilities, but visual reasoning capabilities we can explore more. Modality coverage, it is a static image we can do on a video understanding also, and temporal reasoning also. Scale evaluation, not tested on 70 billion plus parameter models due to computational resource constraints. So we can scale the evaluation, scale the experimentation. So future directions are general purpose teachers, incorporate encoders like intern VIT for broader reasoning improvements, video modality extension, large scale validations with 70 plus billion parameter model. So summary is we have improved across different evaluation paradigms, different tasks like depth, segmentation, counting, uh, and we have got an inference speed up with a data efficient approach. Training samples are 558K only. And this paper published in News 2025. The core impact is vision-centric training with substantially enhancing visual perception in multimodal language models efficiently without sacrificing the regional capabilities, inference speeds, stabilizing a new paradigm for incorporating specialized knowledge in journalist architecture. Thank you. This is the end.